Yeah, the class is supposed to be started at 9:45 or 9:30.
9:30 was the message, sir.
9:30 was the message. Okay. It is supposed to start only by 9:45 and it has to go till 1.5 hours, which is 12:15 or 11:15. So it should go. Fine. Okay. We'll clarify this. Okay. So guys, actually you can take some rest. We'll start the class because I had class till 9:30. I had 10th and I have to start this. We'll start the class by 9:45. Okay, you can take some rest until then. And the class will go on till 1.5 hours basically. 9:45 plus 1.5 hours would be 11:15, I guess. Right? Okay. Okay, guys, good morning. So remember that the class will start from now on. My class will be starting at 9:45. Okay. So the thing is 9:30 only I complete the class. So it may take 5 more minutes for me to, like say maybe like there might be some extra time I have to teach them. So that's why we keep the 15 minutes buffer between the classes. So from now on, the class will start only by 9:45. Okay, right. So let me share my screen. So I actually have to discuss this. Right. So people, we have been seeing this is the thing. No, this is I think the other one to take. Okay. Yeah, this is where we stopped. Right. So guys, just giving you a recap of whatever we have seen. We have seen till now. Okay. Okay, so we talked about solution pressure, osmotic pressure, basically the tendency of the metal. Like if you keep electrolytic conductor and an electronic conductor in contact, you will see that the ions are going to move from the electrode to the electrode is basically the electronic conductor, metal conductor, electrode to the electrolyte, or from the electrolyte to the electrode. Any of this can happen, and that is what is called the solution pressure, electrolyte to electrode to electrolyte, and this is opposite. Osmotic pressure is opposite, right? So again, because of this, there'll be some charge separation, right? Because the positive ions are moving into this, the solution becomes positive and the electrode becomes negative, right? So because of there'll be a potential developed, and that will not be able to measure. All be able to measure will be in the potential difference. If I connect this with something else which has some potential, that potential difference I'll be able to measure. Okay, and then we move on to see what are the different types of cells. There are galvanic cells, electrolytic cells, and galvanic cells. We take spontaneous chemical reactions, right, which are going to be exothermic in nature. So I convert chemical energy into electrical energy. I produce electricity basically from the chemical energy. And then electrolyte process, I'm going to take a non-spontaneous chemical reaction, and it is going, obviously it is going to be endothermic. So I convert electrical energy into chemical energy. Basically, I have to supply energy for these reactions to happen. Right, I have to supply energy for these reactions to happen. So obviously that energy supplied will be in terms of electrical energy. You supply electricity and the reaction will happen, something like that. Okay, and then now we went on to see what are the different specific example of galvanic cell, and the specific example of galvanic cell what we saw was Daniel cell, right? And this is the construction, right? You will have zinc sulfate solution, and you will have zinc rod inserted into this, and then you will have copper sulfate solution, which will have, again, you will have copper rod inserted into it. And this you have to remember, LAO, left anode oxidation. In the left hand side only we'll keep the anode, and then in the anode only oxidation will happen. I told you the chemical reactions which are going to take are nothing but oxidation reduction reactions. Okay, so left hand side anode will be there, and in anode oxidation should happen. Same way for cathode, it will be in the right hand side and the reduction will happen, right? And then you know how what is going to happen here. Basically, this particular half of the cell, this entire circuit, like this one side of the cell, right, is what is called as one half cell. The other side is called another half cell, anode half cell, cathode half cell, right? And you have to understand what are the reactions happening here. Okay, now I told you how do you choose which is going to be the cathode, which is going to be the anode, and then I think we spoke about it here. When I say reactivity, right, when we generally speak about metals reactivity, we speak about electropositivity. Okay, so I think I've mentioned it here. More electropositive element should be in the anode. Why? Because when I say it is more electropositive, that means it can easily form the positive ion. Right? Say sodium will form sodium plus very easily. Zinc will form zinc 2 plus very easily. Correct? Right? So whenever I say electropositive, that means I have more tendency of that particular metal to undergo oxidation. And just now we said oxidation should happen at the anode. Right? So now the more electropositive element should be there in the anode, and the less electropositive or more electronegative element, either of it, less electropositive or more electronegative will be in the cathode. right? And obviously that metal has more tendency to undergo reduction than compared to this metal, right? So I think we even saw some examples. If I have Ag and chlorine, right? Ag and chlorine, obviously Ag has metal, it is electropositive, so I go with anode. Chlorine is electronegative, so I put it in the cathode, right? Okay, so this is what we have. This is how you choose which has to be in the cathode, which has to be in the anode, depending on which can undergo oxidation, which can undergo reduction, right? Okay, and then what will happen? The half cell reaction is like this. Anode half cell reaction, oxidation should happen. So zinc will form Zn2 plus by losing 2 electrons, right? And in the other side, that is the cathode side, you will see that copper 2 plus will accept 2 electron to form copper, right? So you see the electron movement, I think I have mentioned it here. The electron movement is going to be from this side to this side. I think I mentioned it here. This is the direction of electron flow. So obviously the direction of current flow will be opposite, right? And if the current will flow, this bulb which I have is going to glow, right? And then one more thing, what we have here is a salt bridge, right? Now salt bridge, we know why we are using it. I guess I think I've mentioned it here, right? So you will see that there'll be some charges formed here, right? So basically the zinc 2 plus ions, right? I think I've put it here somewhere. Where did I put? Okay, I didn't put. Okay, so I think you can see here, right? The solution is going to become more and more positive, right? Because from here, the Zn2 plus ions are going to go inside, right? The solution is going to become more and more positive. So the solution is becoming more and more positive, and you can see that the electron flow is going to move from this side to this side. So electron has to move from here to here, right? So now if the solution is going to become more and more positive, it is going to become more and more difficult for us to remove electrons, correct? It is going to become more and more difficult for us to remove electron. So now again, in this case, now the copper 2 plus ions are going to go here. It is going to form positive charge. So obviously in the solution, I'll have negative charge, right? So again, you are adding electron this side, right? You are adding electron this side. Already I have so much negative charge. So adding electron to a negative charge is going to become more and more difficult, right? So to overcome all this problem, we use something called the salt bridge, right? And I told you how to make a salt bridge. You take a filter paper, right? And you dip it in some KCl solution or NaCl solution, and then you roll it, right? You roll it like this, and then you keep it across a circuit, right? So what will happen here? There'll be some positive charges formed. So Cl minus will come here and then absorb this positive charge, or say neutralize this positive charge. K plus will go here. It will neutralize this negative charge. Thereby, the electron removal and the electron adding process, right, will become more and more easier. That's why we said that this thing is going to maintain electrical neutrality. That is how it is happening. Okay, fine. And then we went on to see how do you calculate this potential, right? I told you that the potential difference can be measured. This potential difference, we call it as EMF. There is a difference between potential and EMF, but we'll not go to the physics of it, right? So when I say E of the cell, right, the EMF of the cell is always going to be the cathode potential minus the anode EMF. The cathode EMF minus the anode EMF. Or you can even write ER, I can even write like this, ER minus EL. Or again, this is E naught R and E naught L. Right? Okay. So basically what you have to understand is what is the, if it is Daniel cell, right? You have to put the copper's potential here, and anode I have zinc, the zinc's potential here, right? And then what is the specific, what is the thing of this knot? When I put the knot, it means it is standard potential, standard EMF, right? And we know standard EMF means I need to have some standard conditions, 25 degrees Celsius, 1 atmospheric pressure, and all the electrolytic solutions, zinc sulfate, copper sulfate, all of them should be 1 M. Okay, fine. Now the next thing is we went on to see potential. Potential, I told you that I can have two different types of potential, reduction potential and oxidation potential. Now their magnitude is same, right? The magnitude is same, only the sign will be different. Okay, but I told you that whenever I say potential from now on, we are going to speak only about reduction potential. We're going to speak only about reduction potential. So we'll come back to this. Why is it negative? Why is it positive? We'll come to that. Today I will explain you why is it negative, why is it positive for a particular element, right? So, but remember that when I say potential, we are going to speak only about reduction potential. Oxidation potential will not take. Okay, right. Fine. Now the next thing is, how do you find this individual elements' potential? Reduction potential of zinc, reduction potential of copper, reduction potential of aluminium. How do you find? So there is a thing called a standard hydrogen electrode, right? Standard hydrogen electrode. This is the setup. I have a vessel. In this, I have H2O and H2SO4. H2SO4 concentration should be 1 m, and I add only 2 to 3 drops of it. Okay, just to increase the conductivity of water, right? Water is not conductive, right? So to increase the conductivity of water, I add some H2SO4, and then you insert a platinum rod, right? The electrode here. This is the electrolyte. Electrolyte is H2O plus H2SO4. The electrode is my platinum rod. Okay, and then you cover it with a glass tube, right? And I'll have an opening here, right? In this opening, I will give H2. This is the setup. Very simple setup. Okay, fine. Now, how are you going to measure? Now, first thing what you have to choose is whether you're going to put the She in the cathode or whether you're going to put the She in the anode, and that depends on for which metal you are finding the potential. Now, if it is zinc, I know zinc is more electropositive than hydrogen, right? So I put zinc in the anode side and She in the cathode side, right? Okay, now the anode reaction is going to be simple. Zinc again will form 2 plus 2 electrons, and in cathode, I have reduction should happen. So H plus will accept 2 electrons to form H2. There are only 2 components here. H plus is going to come from the electrolyte. H2 is coming from this, from the opening. Okay, now if it is oxidation, I should write the opposite reaction. Anyways, now the overall reaction, you just have to add these 2 reactions and write it. Okay, now what we said that obviously the potential of, now one more thing what we'll do is instead of the bulb, we put a voltmeter. Okay, now this voltmeter will measure the potential difference between the anode side and the cathode side. Very simple, right? So you can see E0 cell is going to be E0 cathode minus E0 anode. We already know this, correct? Now what you have to understand is, guys, for standard hydrogen electrode, the reduction potential is 0. Okay, I told you that She is going to be acting as reference, correct? So for that, E0 CHE, SHE, so She is going to be 0 by default. Okay, so what is going to happen if I have the voltmeter and that voltmeter will show some reading? That is what is E0 cell. Okay, now in the cathode side, I have the She, so that is going to become 0. And whatever the potential which is shown by the voltmeter will be the potential of the anode. And in this case, it is going to be zinc rod. I mean, zinc rod in the sense zinc system. Okay, so by this, we'll be able to find for all the elements. Say if I want to find for copper, I will put She this side and then copper this side. Again, same thing. She will become 0. Whatever the potential the voltmeter shows will be the reading of the reduction potential for copper, right? And then we went on to see how do you represent a cell, right? Representing a cell is also very important, guys. So I told you bar represents the transformation. Zinc, you already started with the left-hand side, that is the anode side. You have to see what is happening. Zinc is becoming Zn2 plus. So I put a bar, zinc bar, Zn2 plus, and you have to mention whenever you talk about the electrolytes, ions, you have to talk about the concentration. Obviously, it is standard hydrogen electrode or standard EMFs. So I put 1 m only. Okay, and this double bar represents Solbridge, right? And then we went on to see that H plus is becoming H2. You can see H plus is becoming H2, bar H2. And obviously H2 is a gas, so you have to mention the pressure. That is 1 atm, and H plus will be the solution. So you have to mention the, what is that, concentration, that is 1 m. Okay, fine. Again, I told you that if it is going to be copper, it is going to be this cell representation. We saw this is how exactly we do it, right? This represents transform, this represents Solbridge, right? And then how do you represent the EMF, right? Since we're talking only about the reduction potential, when you write E0, this is how you write Zn2 plus becoming Zn, irrespective of whether that particular species undergoes oxidation or whether it undergoes reduction, right? But you will write only the reduction transformation. Cu2 plus bar Cu, H2 bar H plus bar H2, Zn2 plus bar Zn. Whenever you write the EMF, that is how we write. Okay, fine. Now that we know all the reduction potentials of all the elements, right? Then we went on to see what is this electrochemical series. Electrochemical series is nothing but arrangement of elements with respect to the E0 values, right? So either you start with highly electropositive element and end with highly electronegative elements, or you can even do the opposite. Okay, and at last, I told you that this equation is very, 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 very important, right? Now I'm going to connect my potential values, reduction potential values with this delta G. Okay, and the equation is delta G is equal to minus NF E0. Okay, and the Z naught is the reduction potential. F, I told you, is Faraday. 1 Faraday is nothing but charge of 1 mole of electron. We calculated it, right? We calculated approximately it to be 96,500. F value, we write the F value here. The F value is 96,500. The unit is very important, coulomb per mole, because we define 1 Faraday as like this, charge of 1 mole of electron. Right, a charge of 1 electron is this much. 1 mole of electron will contain Avogadro number of electrons. So if you multiply these two, you are going to get 96,500. Okay, and this N represents the number of electrons involved. For example, if for it is zinc, it is 2. For copper, it is 2. For aluminium, it will be 3. Right, so like that, that N represents the number of electrons. Okay, this is what exactly we saw last class. Any questions, guys? Any questions from any of this, whatever we saw? Just a quick recap of whatever we saw. Is there any questions, guys?
Sir, what is that E naught Z10 2 plus bar Z10, sir?
Oh, nothing. That, see, we write, instead of writing reduction potential of zinc, right? The representation goes like this: E naught Zn2 plus bar Zn. That's it. This E naught represents the EMF. Since we're talking about reduction potential, we always write only in the form of reduction. Obviously, you can understand the oxidation state is 2, here it is 0, right? So you always write like this: E naught Zn2 plus bar Zn. Or if it is going to be, say, for She, if you want to write, it will be E naught H plus bar H2. Say, if at all you want to write for chlorine, it will be E naught Cl2 bar Cl minus. Hope you understand. We always write only in terms of reduction. You can see all of this, whatever I've written, we write only in terms of reduction. Why? Because we're speaking about reduction potential, not the oxidation potential.
Okay,
yes,
sir.
understood?
Understood, sir.
Yeah, cool. Yeah, so yes, any other question? Yeah, please.
So for Zn, we put Zn2 plus bar Zn, right?
Yeah, yeah.
And for chlorine, why aren't we putting Cl minus bar Cl2?
See, it has to be reduction, correct? Now, what is the oxidation state of Cl2? Oxidation state of Cl2 is what?
0, sir.
0. What is the oxidation state here?
-1.
For Cl minus, -1. So what is happening to the oxidation number? Oxidation number
reduced.
Is reducing. So obviously, that's why we write this.
Okay, sir.
Okay, right? Fine. So fine, we'll continue with this, guys. What is this equation? Delta G is equal to minus NF E naught. We'll concentrate on that. Okay, I hope. If there are any other question, please do ask. Okay. Right, so let me make some page, add a page. Okay. Right, so today is, I think, 20th. 20, no, this is 12. 2006. Oh, fine. So we'll just start with the equation. I don't want black. I want this only. Okay. So I'll just write the equation again. Delta G naught is equal to minus NF E naught. This is a very, 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 very important equation. Okay, fine, guys. Okay. Now, what is the importance of this equation? Right. Now, please understand, for a spontaneous reaction, right? For a spontaneous reaction, how should be the delta G value? For a spontaneous reaction, delta G should be
less than 0.
Absolutely right. Delta G should be less than 0. Okay. Now, if you look at the equation here, right? If you look at the equation here, if I want, say, for example, any particular oxidation reaction or reduction reaction, whatever I have, if I want delta G to be negative, how should be the value of E naught? From the equation, can you tell me?
Positive.
These two are correct, right? These two are constants. N is a number, F is also a number, but this is what is going to decide whether that particular reaction is going to be spontaneous or not. And if I know that for spontaneous chemical reaction, delta G should be less than 0, obviously the E naught value should be greater than 0. Right? And delta G value should be greater than 0. Okay, fine. Now keep this in mind. For a spontaneous reaction, I see again this potential what we are talking about can be oxidation potential or it can be reduction potential, right? So that also you keep in mind. This E naught, which I'm telling about, it can be oxidation potential or reduction potential. Okay, now look at this reaction. Say I have zinc plus copper sulfate becoming zinc sulfate plus copper. Okay, now first things, do you think this reaction is spontaneous or not? Is it a spontaneous reaction? Okay, maybe I'll talk like this. Maybe if I write sodium reacting with copper sulfate to form sodium sulfate plus copper, is this reaction spontaneous?
Yes, sir.
Okay, how do you decide this, whether it's spontaneous or not?
So because sodium reacts vigorously, sir.
Correct. Basically, sodium is more reactive than copper. As simple as that. Sodium is more electropositive than copper, and that is why this displacement reaction is happening. Same thing I can say here also. Correct. Zinc. Yeah.
Sir, should delta G be lesser than 0 or delta G not?
Oh, anything can delta G naught or delta G is fine. I'll tell you the difference. Delta G naught is basically standard. Standard gives free energy. Delta G, if I write it, is non-standard. That's it. Like only the conditions will vary. Nothing else. Okay. Right. So just now we said that this reaction is spontaneous because I know sodium is more reactive than copper. So obviously I know zinc is again more reactive than copper. Right. So this reaction is also spontaneous. No doubt about it. Okay. So what is that? If I just look into each and individual element, what is happening to the individual element, what I understand is zinc is becoming Zn2 plus by losing 2 electrons, and copper 2 plus is accepting 2 electrons to form copper. Correct. Now say if I speak about the potential, just give me a moment, there is a lot of background noise. 1 second. Okay, fine. Now it's better. Right. So we are talking about these two reactions. We spoke about this reaction, and I'm writing the half reactions basically. What is happening to zinc? What is happening to copper? That's what we are looking at here. Okay. Now tell me, guys, this individual reactions should be spontaneous. Only then the overall reaction would be spontaneous. Make sense? Correct. These two individual half reactions should be spontaneous. Only then the overall reaction will be spontaneous. Correct. So basically what I'm telling is this zinc becoming Zn2 plus is oxidation. Correct. Right. This zinc becoming Zn2 plus should be oxidation, and this is a spontaneous reaction. Right. So for this, okay, maybe I'll write it separately. I have zinc becoming Zn2 plus by losing electron. I am telling you that this reaction is spontaneous. Correct. Okay, and then now obviously if it is spontaneous, delta G naught or delta G should be less than 0. If I want delta G to be less than 0, if I take some potential here, E naught, this E naught should be greater than 0. Correct, delta G is equal to minus NFE, or delta G naught is equal to minus NF E naught. Now I want this E naught to be greater than 0, only then the delta G will be positive. Okay, but if you remember the electrochemical series, the value for zinc we got E naught Zn2 plus bar Zn we got was a negative value. Do you remember this, guys? Do you remember that I got a negative value for zinc? Does everybody remember? Okay, nobody remembers? If I show you the values, 1 second, wait, let me show you. Something I will take. Okay, right. Now look at this. Where is zinc? Zinc is here. The value is minus 0.76. Okay, the value is minus 0.76. But what did I tell you? I told you that the value we should take, value we should be getting, right? Value we should be getting for this reaction to be spontaneous is that I should have the E naught value to be greater than 0. That means it should be positive. But what is the value I'm getting is negative. That means this reaction is not spontaneous. Is it something like that? So this makes us ask questions, right? And that is exactly where the concept of oxidation potential and the reduction potential comes into the picture. Okay, now look at this, guys. This is oxidation reaction, right? This is oxidation reaction. So when I tell you that the potential should be greater than 0, for this, I am talking about oxidation potential to be greater than 0. Only then this oxidation reaction will be spontaneous. Again, I repeat, right? The thing is, this zinc becoming Zn2 plus 2 electron is a spontaneous reaction. No doubt about it. Okay, and according to this equation, delta G is equal to minus NF E naught. If it is a spontaneous reaction, delta G should be less than 0. And if I want delta G to be less than 0, the E naught value should be greater than 0. No doubt, right? But just now I showed you that the potential value we get is a negative value. That means it is not spontaneous, but it is not like that. What we understand here is that the potential we are taking, that is, when I say that the potential should be greater than 0, I am talking about oxidation potential. I told you oxidation potential and reduction potential will have same value, except that their sign will change, right? So yeah, if I take the oxidation potential, that will be greater than 0, and that will make delta G to be lesser than 0. Okay, but what did I tell you? By default, we will take only reduction potential values. We will not consider oxidation potential. Okay, that is the reason why I say that this value is negative. Okay, now what do you see? I write like E naught Zn2 plus bar Zn, right? So how do I write the reaction for this reduction reaction? Zn2 plus 2 electrons will form Zn. This is how we write, looking at this equation, reduction potential, the representation. This is what we can write, right? Zn2 plus 2 electrons will form zinc. And this, please understand, is a non-spontaneous reaction, right? This is a non-spontaneous reaction where delta G will be greater than 0. And this is for delta G of reduction. And here we're talking about delta G of oxidation. Different reaction, basically the opposite reaction we're talking about, right? Forward reaction, backward reaction is what we're talking about. Obviously, if the forward reaction is spontaneous, the backward reaction is obviously non-spontaneous. Okay, so now we take this reaction, reduction reaction. I know it is non-spontaneous. Obviously, delta G will be greater than 0. So obviously, the E naught reduction will be lesser than 0. I hope it all makes sense. Right? Even though this reaction is spontaneous, right? But why do I have a negative value is because this reaction is an oxidation reaction. And what potential we are taking is a reduction potential. And that's the reason why we have reduction potential value of zinc to be negative. And obviously, if you take the opposite process, that is zinc becoming Zn2 plus 2 electron, that reaction will have delta G to be less than 0. But the potential we take at that time would be oxidation potential and not the reduction potential. So maybe if we can write like this, E naught Zn bar Zn2 plus, I write. Okay. Now see, please understand oxidation potential and reduction potential will have same magnitude. Now you saw it as now reduction potential is minus 0.76. Oxidation potential will be plus 0.76. Plus 0.76. That's the only thing. Right. Now how we interpret whether oxidation or reduction is based on this delta G. Okay, right? Is there any question, guys? Hope you understand what is the difference between oxidation potential, reduction potential, what is the use of delta G? Okay, right? All these things must be in your fingertips. But again, nobody will ask you the reason behind why are we taking reduction potential, how is it less than 0 and all that. Nobody will ask you, but it's good to know what exactly is happening here. Okay, it is all because I want to follow some convention. I want to take only the reduction potential value. I don't want to confuse with the oxidation potential, right? So that is the reason why if I have a spontaneous oxidation reaction, then the reduction potential value will be negative. Okay, but if I have a spontaneous reduction reaction, like say I have Cl2 accepting 2 electron to form 2 Cl minus. This is a spontaneous reduction reaction. Right? So again, for this delta G will be less than 0. And I know delta G will be equal to minus N of E naught. this E naught will be greater than 0. Now, why it is greater than 0 by itself is because we are considering reduction potential. Okay, I hope it all makes sense, right? What is the use of delta G? What is the use of reduction potential? Okay, right? I hope it's very clear, right? Okay, fine. Moving on. Right now, if I take both the reactions, right? Say now I have zinc becoming Zn2 plus 2 electron, copper 2 plus accepting 2 electrons to form copper. Right now we are talking. Now forget about oxidation potential. We are not anymore going to speak about it. Forget about it. Right. So now I want to write the E naught value here, which is minus 0.76, and I want to know what is the value for copper. Let me look into it. Copper. Yeah, copper is plus 0.34. Okay, you look at here. Copper is plus 0.34. Right. Let me write it there. 0.34. Okay, fine. Now, I write E naught of the whole cell. I'm talking about Daniel cell. I know I have zinc sulfate, copper rod, zinc rod, everything is there. So I know it. How will I write? It is going to be E naught copper 2 plus bar copper. Please understand it is cathode minus anode. In cathode, I have copper. In anode, I have zinc minus E naught Z2 plus bar zinc. No issues. Now I substitute the values here. E naught Zn2, I mean Cu2 plus bar Cu is 0.34 minus of what is the value for zinc? Zinc is minus 0.76. Right. So if you calculate, it would be how much? 1.1 plus 1.1 volts. Right. So if I talk about delta G naught of the cell, which is equal to minus NF E naught of the cell. Now, if at all I want the cell to work, right? If at all I want the cell to work, that means if at all I want to produce something like the bulb should glow, all those things, this delta G should be less than 0, right? If I want delta G to be less than 0, this E naught value, E naught of the cell should be greater than 0. And that's exactly what we find here. Okay, that's exactly what we find. The E naught of the cell is greater than 0. Right. Now, same thing if you would have taken oxidation potential, people. This would have come here and this would have come here. And okay, maybe I'll write it again. See, if I write it in terms of oxidation potential, E naught cell is equal to E naught Zn2, Zn bar Zn2 plus minus E naught copper bar copper 2 plus. Right. Now, see, please, we are talking about oxidation potential here. So if it is minus 0.76 for reduction potential, it is plus 0.76 for oxidation potential, minus, this is plus 0.34 for copper in terms of reduction potential. Here it will be minus 0.34 for this. Again, you will get the value as 1.1 volt. Again, you will see that the delta G will be less than 0. That means the cell reaction will happen. Right. So what you understand from here is, guys, either you use reduction potential or you use oxidation potential, the value you are going to get is same. The cell representation is not going to change. The delta G value is not going to change. Everything is going to be same. But just to follow some convention, just because someone else, like everybody is following that, we will also follow the same thing, that we will use only reduction potential values.
Sir?
Okay. Yeah.
So for oxidation potential, the E naught cell value is E naught anode minus cathode. Sir.
Absolutely. I forgot to think. So if I talk in terms of oxidation potential, it will be E naught oxidation of anode minus E naught oxidation of cathode. Yes, that's absolutely true. That is why, to avoid all these confusions, we use only reduction potential. That is E naught reduction potential of cathode minus reduction potential of anode. As simple as that. Right? But nothing is going to change. You don't have to worry about why is it negative, why is it positive. All this will be taken care by delta G. Okay? You do not have to worry about this. You are not going to use this oxidation potential anymore. This is all just to give you a flavor that this also exists. Okay? I think I've made my point very clear. Is there any questions, guys? Yeah. Okay, fine. So I hope there are no questions. We'll move on. Right. Cool. So now we know how to calculate the potential, what is reduction potential, how it is connected to delta G. All these things are in our fingertips now. Okay, fine. Now we are going to move away from standard conditions, right? Instead of we write E naught, correct? We write E naught means standard conditions, which are I already mentioned. Say the electrolyte concentration should be 1 m, the reading should be taken at 25 degrees Celsius, and the pressure, if I use any gas, of the pressure of the gas should be 1 atm. All these are standard conditions, right? Say what if I move away from this, right? What if I take 2 m and I do this thing at 30 degrees Celsius and the pressure of some gas is say 2 atm, right? At that time, I will not be able to use this naught. Okay, I will not be able to use this E naught. All I'll write will be E. That means non-standard. Right? That will be non-standard. Okay, but there is going to be a connection between this and this. Right? Actually, if I know this E naught, that is, if I know the standard reduction potential, there is going to be some way that I will be able to find this value. So if I change any of this, right? If I change any of these factors, I will be able to find what will be the non-standard reduction potential. Obviously, you will not be able to do every time with the same requirement, right? 1 m, everything. According to the application, you will change it, right? So if you change it, is there any way by which I'll be able to find this particular non-standard reduction potential or non-standard EMF for that matter, right? There is a way. And for that, we have to go back to thermodynamics, right? Now, hope you all remember this equation, people. I have delta G, which is non-standard Gibbs free energy, will be equal to delta G naught minus or plus. It's plus delta G naught plus RT ln QC. Do you remember this equation? Anybody remember this equation?
Yes, sir.
Okay, something little bit, correct. Okay, so delta G is your non-standard Gibbs free energy. This is standard Gibbs free energy. R is universal gas constant. T is temperature in Kelvin. Ln is ln, logarithm, natural logarithm. What is QC? What is QC, guys? QC? Nobody remembers QC. Equilibrium chapter? QC? Think about it. I'll give you a minute.
Capacity.
Oh, no. That is okay. That is C, Kanna. That is just C. Heat capacity. That is from thermodynamics. QC, just Q. Or if you don't remember C. Yeah, what is it?
Reaction.
Reaction. Right. So anyways, I'll let reaction what, Kanna?
Reaction quotient, isn't it?
Correct. This is called reaction quotient. Right. So it is very similar to the equilibrium constant. Right. Say now I write A plus B giving C plus D. I write QC as basically the concentration of products divided by the concentration of reactants. Right. Now this is QC. Even equilibrium constant will also be the same thing. But what is the difference between equilibrium constant and this, guys? Equilibrium constant also will be products raised to some powers divided by reactants raised to some powers. This also is the same thing. So what is the difference here between QC and KC? Or reaction quotient and the equilibrium constant? What is the difference? I'll write QC also like this, right? QC, KC, right? KC will also be equal to C into D divided by A concentration into B's concentration. If we write like this, then what is the difference between QC and KC is what I'm asking. Anybody knows?
So QC determines the direction of reaction.
Okay. Correct. It does determine the direction of the reaction. Based on what?
Based on KC, QC decides.
Based on KC, right? Based on whether QC is greater than KC or QC is less than KC, I will be able to tell, say, it is going to move in forward direction, or in reverse direction, right? So the main difference here is that, guys, the concentrations you use here and here are not same, in the sense that this can be any concentration, at any point of time, say at the starting of the reaction, in the middle of the reaction, at the end of the reaction, I can use whatever the concentration available at that particular point of time here in terms of QC, right? But in Kc, we have to write only the equilibrium concentration. After the reaction has reached equilibrium, whatever is the concentration of A, B, C, D, that value only you will keep here. I think some bell is ringing in all of you. All this you have already learned, right? So this concentration which we write here can be any concentration, starting, between, end. But Kc will always, the concentrations we always take only at equilibrium, on and only at equilibrium. Okay, this can also be at equilibrium. No, there is no restriction on this. If the concentrations we take are at equilibrium, then QC will become equal to Kc, and that's when we say that the reaction has reached equilibrium. Correct? Okay, we'll keep on checking the value of QC, and by the time QC becomes Kc, the reaction stops. That means what? The reaction has reached equilibrium. That's what it means. Okay, right. Now why did we start all this? I told you that we are going to have a connection between this standard reduction potential to this non-standard reduction potential, and for that we are going to take use of this delta G. Okay, so delta G is equal to delta G naught, that is standard gives free energy, plus RT ln QC. QC is the reaction quotient, and just now we saw what is reaction quotient and what is that Kc. What is the difference between them? Okay, now you already know this equation, that is delta G. Okay, actually I'll write it again. So you have basically delta G is equal to delta G naught plus RT ln QC, and you also have this equation, delta G is equal to minus NFE, and delta G naught is equal to minus NFE. So basically, if I use standard gives free energy, I use standard potential. If I use non-standard gives free energy, I use non-standard potential. As simple as that. Right? No issues. Okay. Now let me plug in these values in this equation in terms of delta G and delta G. Let me plug in the value. So what will happen? I'll write minus NFE is equal to minus NFE naught plus RT ln QC. This stays same, no doubt. Okay, now what I do is I will divide the entire equation by NF, minus NF. Okay, I'll divide the entire equation by minus NF. Okay, so if I divide the entire equation by minus NF, can I write like this? E is equal to E naught, because minus NF gets cancelled, plus RT by NF ln QC. Now you see why did we start all this? We started all this to get a relationship between E naught and E, and we got it. Right? E is equal to E naught. Oh, a small mistake is there. We are dividing it by minus NF. So this plus will become minus, correct? So this is not plus. This is minus. Okay. So if at all I want to write it very, very properly, I write it like this. E cell, right? E cell is the EMF of the cell, and non-standard condition will be equal to E naught cell minus RT by NF ln QC, right? And this equation is a very, 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 very important equation. And this equation's name is what is called as your Nernst equation. Okay, this equation's name is what is called as your Nernst equation. Very, 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 very important with respect to problem solving. At least you will find 1 or 2 questions coming in your board exams for sure, without any doubt. Cool. Right? So hope you understood the derivation is not important, guys. Right? In your book also there will not be any derivation because you don't have to remember the derivation. But it's very easy, right? You just have to plug in delta G and delta G naught in terms of NFE and NFE naught, and then you're going to get this one. Divided by minus NF, and you're going to get this. Okay, and this
the ln values.
We should find the
ln value.
Yes. Okay, fine. Wait. Like we actually can modify this equation a little more. I can write E cell is equal to E naught cell minus. Now, if at all I don't want to use natural logarithms, basically this is log means log to the base E, right? They converted it log to the base 10. So what do we do generally? If I want to convert ln to log, log, what do I do generally? This is log to the base E, this is log to the base 10. What do we do generally to convert this? So many times you've done in physics, so many times we did in chemistry in 11th class. What do we do generally? Okay, remember that ln value, if you multiply it by 2.303, right? 2.303 into the ln value will give you the log value. Okay, so if I write proper equation, it is going to be 2.303 RT divided by NF log of x. This is what is the perfect non-state equation. Okay, now here the thing is, it is log to the base 10. Right, hope you all remember, guys, a log value will have a upper component and a base component. I write log A to the base B, something like that. Okay, this base is what is going to determine what kind of logarithms you use, natural logarithms or your log to the base 10, right? So anyways, so this is what is the equation. So now you have a connection between the EMF of the cell at non-standard condition with the cell which is in standard condition. Okay, now this equation can be further more simplified. Okay, now how it can be further more simplified, let me tell you. Right now, 99% of times, right, 99% of times, the reaction will happen only at 25 degrees Celsius. The reaction would happen only at 25 degrees Celsius. Okay, now if T is 25 degrees, that is 20, you should not write 25 degrees Celsius, so you convert it to Kelvin. Right, so it is going to be 298 Kelvin. T is 298 Kelvin. R value is 8.314. Why you use 8.314? Because we are getting it from delta G. Delta G will be in terms of energy. Whenever you use energy in terms of joules, we write 8.314. Hope you remember all of this, guys. I told you whenever, like 11th is very, 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 very important. Okay, if your concepts are not very clear in 11th, I told you that you will little suffer in 12th. Right, so like I think you're able to see what I was telling at that time. Anyways, so R value is 8.314. N value we don't know, depending on the reaction. I know F value also. F value is 96,500. Right, so if you substitute all these values to this equation, 2.303, 8.314, 298 Kelvin, and 96,500, you are going to get a simplified equation like this. The equation goes like this: E cell, all right, E cell is equal to E naught cell minus 0.059 by N into log of QC. Okay, the 0.059 came from the calculation by putting in all these values, and N value depends on what reaction you're going to take. Okay, N value depends on what reaction you're going to take, and QC again will depend on what reaction you're going to take. Okay, right, 99% of times you will use only this equation, right? And if they don't mention anything about the temperature, right, sometimes they will not even give temperature in the question, right? So by default, right, temperature is 25 degrees Celsius. If they don't give you any temperature, assume the temperature will be 25 degrees Celsius, and you can directly use this equation. You don't have to use this equation which we wrote here, this equation. This is the entire equation. But if the temperature is 25 degrees Celsius and other things are constants, then you can easily get this equation: 0.059 by N into log of QC. Okay, right, fine. Now let us concentrate on this QC for a while, because depending on the reaction, the QC will change, the N value will change, and you have to be very, 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 very careful in this. Okay, now, okay, before we move on to this E naught cell can be easily calculated, right? Why? Because this can be calculated on the spectrochemical series. How we calculate E naught cell? E naught cell will be E naught cathode minus E naught anode. right? This can be easily calculated. E naught cell can be easily calculated, but you cannot calculate the same way for E cell. Okay, so you calculate E naught cell like this. What, depending on what is the cathode, depending on what is the anode. I know the potential from the table, and don't worry, they will give it to you in the questions. Okay, there are standard reduction potential values of the two elements. Say if it is zinc and copper, right? You will be able to find that values will be given. So that now E naught cell can be easily calculated from the given values. Okay, then from this you have to calculate your E cell using this equation. Okay, now this you have to remember, guys. E naught cell can easily be directly calculated by using this equation. After calculating E naught cell, then we go for finding the E cell value by the help of Nernst equation. Okay, now this point I've made very clear. Now we'll move on to see what is this N. Obviously, N is your number of electrons involved, and QC is the reaction quotient, but you have to be very, very careful. Okay, fine. Now, guys, if I have a cell, I represent the cell like this. Okay, now I say I have, say like this, chromium 3 plus, or no, wait. I start with something simple. Okay, so now I'm going to take zinc and Ag, right? So from your knowledge, tell me which I have to use as cathode, which I have to use as anode.
So zinc is anode.
Okay, and obviously Ag is cathode. Obviously, now I think you're very, very, very comfortable with that now, right? Depending on which is more electropositive element will go to the anode, less electropositive element will go to the cathode. So obviously zinc has to be there in the anode. This will be in the cathode.
Sir, but
Right.
Ag is sir, but Ag should be an anode, no, sir, because Ag is zinc is non-metal and Ag is a metal.
No, who said zinc is a metal? Ag is also a metal.
Okay, sir.
And obviously zinc is more electropositive metal than this thing. What is that? Ag. And that is why we use, that's why, since silver is very less reactive, that is why we use in wires, your whatever insulation stuff, right? Not insulation, for conducting stuff. Your wires and all you use this thing only, because even when the current passes, even when some heat is there, the Ag will not react. But zinc, if it is there, aluminum wires, if you have, all these will react easily. Okay, anyways, right? So this is the anode, this is the cathode. I will give you a minute. Okay, I will give you a minute to write the cell representation. Right? Anode half reaction and the cathode half reaction and the overall reaction. Right? I'll give you 2-3 minutes time. I want you to write all of this. Write this and keep. Okay, the cell representation. How do you represent the cell if I have zinc and Ag? What is the anode half reaction, cathode half reaction, and the overall reaction? I need to know. Go for it. Okay, I think you should have been able to write at this particular amount of time given. Okay, fine. So the cell representation will go like this, right? So I know zinc will form Zn2 plus, double bar, Ag plus will form Ag. Very simple. Right, again, I didn't give you any concentrations and stuff. If I gave you concentration, that also you will include in the cell representation. Okay, fine. Now anode half reaction is very easy. Zinc will form Zn2 plus by losing 2 electron. Cathode half reaction, Ag plus will accept 1 electron to form Ag. Okay, how many of you got all these three correct? Okay, 1,
Got it, sir.
3,
Got it, sir.
okay, 4. Fine, good, right? So this is very easy, right? So you have to write, maybe if you write this first and you write the cell representation, is very little more easier. Is it not? You have to write cathode reaction, anode reaction, then you go for cell representation. It's very easy because you can understand what exactly is happening, what is changing to what. Okay, fine. Now, guys, you have to remember one thing about overall reaction. In the overall reaction, there should not be any electron present. No electron should be present in the reaction. When you write the equation, right, there should not be any electron present. Okay. Now for that, what should I do? Now you see, in case of correct, right? In case of zinc and copper, right? Zinc lost 2 electron, copper accepted 2 electrons, so 2 electron get cancelled when you add these two, right? But when you add these two now, here I have 2 electron lost, but only 1 electron accepted. So there will definitely be 1 electron coming in the product side because 2 electrons are in the product side. 1 electron will come in the product side. I don't want that. Okay, so what will I do is I will multiply this reaction by 2, right? That is the cathode half reaction by 2, so that I have 2 electrons here and 2 electrons here. So when how it will become then? It will become 2 Ag plus 2 electrons gives 2 Ag. No issues. Okay, now when you add these two reactions, 2 electrons and 2 electrons will get cancelled. So the overall reaction is like this: zinc plus 2 Ag plus gives zinc 2 plus 2 Ag. This is how we write the overall reaction. Please remember that in the overall reaction, that is the summation of anode and cathode reaction, there should not be any electron present. If you find the electron present, that means you did something wrong, or you have to multiply by something, or something you have to do so that you don't have any electron in the overall equation. Okay, right. And then what you have to understand is we are going to write the QC. I told you that we are going to concentrate on this QC and your N, correct? Right. So after multiplying, right? For example, if I speak about the N value here for this, right? Say now in the first case, I had 1 electron. In this case, I have 2 electron. Now what you have to understand is when you multiply by something and you cancel it, right? Right. What is the number you cancel? Say it is 2 electrons cancel or 3 electrons cancel, something like that. Whatever the number which is getting cancelled, that is the N value. 2. In this case, it is 2. So 2 electrons lost and 2 electrons gained. So the N value will be 2, not 4. You should not write it as 4. Right? The N value here is 2. Okay. Now that is one thing. When I talk about QC, right? Remember, QC you have to take only from the overall equation. You should not write from cathode. You should not take from anode. You have to take it only from the overall equation. Please remember this. Okay. Now I want to write the QC for this particular equation. QC for this particular equation, the overall equation which we have. Okay, I'm going to write like this: zinc's concentration. Oh, wait, I'm sorry. This is products by reactants. Okay, QC is basically products by reactants. So what do I have? Zn2 plus in the product side, Ag in the product side, divided by zinc in the product side, Ag plus in the product side. Now, there are 2 mistakes in this whatever I wrote. What are the 2 mistakes? In this QC equation,
2 should come as the power of Zn.
Absolutely. 2 should come in the power of Zn.
Zn2 plus.
Zn2 plus. Do I have to put 2 based on what is the charge or anything else?
So I'm not very
AG
one second, wait. So if I write AA plus BB giving CC plus DD, how will you write QC for this? First tell me.
Capital A into
Capital C power small c, capital D power small d, divided by capital A power A, capital B power B. This is how we write, right? So what are these small a, small b, small c, small c? Are they charges or what are they called as? What are these?
Coefficient.
coefficients.
Stoichiometric coefficients. These are what are called as stoichiometric coefficients. Okay, so the concentration has to be raised to the powers of their stoichiometric coefficients. Okay, so this 2 plus or 1 plus what you have does not matter. That is a charge. But what you have to see is the coefficients. Here the coefficient is 1, here the coefficient is 2, coefficient is 1, coefficient is 2. Right? So the powers has to be raised for 2 of them. So obviously AG plus square will come and then AG squared will come. Right? Okay. One mistake done. One mistake you found out. What is the second mistake? So the clue is, remember what is the state in which zinc and Ag will be present? What is the phase or what is the state in which Ag? Okay. If I have solid state, then what should I do? In the QC equation, if I have pure solids or pure liquids, what should I do? Should I include them or should I not? Yes, somebody is trying to say something.
included. So.
Okay, why it should not be? I understand that it should not be included. Why it should not be included?
Constant always.
Constant. Okay, it is a constant. What is the value of the constant? Okay, so these are all. Okay, fine, no issues. So the thing is, guys, when I have pure solids or pure liquids, how will I talk about concentration of them? There should be some solute. There should be some solvent. Only then I can form a solution. And then for the solution, I can speak about the concentration. Yes, agreed. Now, if I have a pure solid or pure liquid, how will I even form a solution? And if I don't form a solution, how will I talk about concentration? Okay, so whenever you see pure solids, whenever you see solids, especially you will find only solids coming in electrochemistry most of the time. So whenever you find solids, remember that the active mass is 1. Hope you remember what is active mass. Active mass is the mass which is actually taking part in the reaction in the form of concentration or say in the form of your pressures, partial pressures, all that. So anyways, so what you have to understand is when you have solids or liquids, we generally take the concentration as 1. That's constant value. We take it like that. And that is why we don't include it. So now this equation, if I write it properly, QC will be equal to the product I have Zn2 plus, right? I don't represent Ag because it's a solid. Again, zinc I don't represent because it's solid. But what I have is Ag plus and I have to put a square. Okay, right? So this is how we write QC. The concentration, the powers are very, 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 very important. If you miss the overall equation, say if you miss this multiplication here, right? You multiplied by 2 and you got the overall equation. If you forgot to multiply this by 2 and you directly write and you take the QC value and you take the QC value and put it in the Nernst equation, everything is wrong. Totally, absolutely, it will become wrong because of a very, very small mistake that you didn't multiply it by 2. Okay, fine. Now I'll give you one more example. Let me see if you can do this. Okay, so I have chromium 3 plus and I have say Zn. Okay, not Zn. I will take copper. Okay, so I'm going to take why am I writing chromium 3 plus is for your understanding, right? Basically, I'm going to take chromium and copper. Okay, so chromium is going to be the ion it can form is 3 plus. Remember that chromium ion can form 3 plus. Okay, and copper ion I know is going to form copper 2 plus. Right. Now, obviously, remember that chromium is more reactive than copper. So this will be in the anode and this will be in the cathode. Right. So like this, what I have to do, again, the same thing, cell representation, anode reaction, cathode reaction, overall reaction, and the QC and the N values, all things I want to know. Go for it. I'll give you a few minutes. I'll give you 2-3 minutes, right? First, write the cell. Maybe first you write the anode reaction, then the cathode reaction, then you go for cell representation, then you go for overall reaction, and then you tell me what is the N value and what is the QC. Like how will you write QC? Go for it. We'll give 1 more minute. I will write this.
Done, sir.
Fine, okay. We will do this. Okay, so obviously I told you that chromium is more reactive than copper. So obviously that will come in the anode, that is chromium will come in the anode, and in the cathode I'll have copper. Okay, so now in anode I know oxidation has to happen. So I'll have Cr forming Cr3 plus 3 electron. Guys, always remember anode oxidation. So here the oxidation state is 0, here it is +3. Increase in oxidation, increase in oxidation number, oxidation. Okay, anyways. So now in the cathode, I have copper. So copper 2 plus will accept 2 electrons to form copper. Again, I go for reduction. Here it is +2, here it is 0. So decrease in oxidation number, reduction. Okay, fine. Now I want to write the O. Okay, before that we can go for cell representation. It's very easy, right? So what is happening? I start with anode Cr bar Cr3 plus double bar Cu2 plus bar Cu. Right. I hope, okay, I hope this particular time, all of you should have gotten this particular 3, like this 3 things, that is cell representation, anode reaction, and cathode reaction. Everybody must have gotten it by this time. Okay, fine. Now, when I go for the overall equation, right now you see here I have 3 electrons lost and here I have 2 electrons accepted. Correct. So I have to do something so that these 2 gets cancelled, and the easy thing I can do is multiply this reaction by 2 and this reaction by 3. So that I'll have 6 electrons here, 6 electrons here, 6 and 6 electron will get cancelled. Okay, fine. So if I write this now, I will have 2 Cr becoming 2 Cr3 plus 6 electrons, and this will become 3 Cu2 plus will accept 6 electron to form 3 Cu. Right now, when I write the overall equation, this and this gets cancelled. So I will have 2 Cr plus 3 Cu2 plus gives 2 Cr3 plus 3 Cu. No problem. Okay, fine. Now first tell me what is the N value?
6.
6. I told you what, I'm sorry, and n value 6, right? Whatever you cancel, that will be the n value, right? You cancel 6 and 6, so the n value is 6. Okay, right. Now when I write the QC for this, okay, it would be what? Again, I don't take this one because it's in solid state. I don't take copper. Again, this will be in solid state. The only thing I'll take is this and this, nothing else. Cr solid state, copper solid state, I don't take, right? So the QC, I will write it as in the product, first product comes. So Cr 3 plus concentration, the whole squared, divided by Cu2 plus concentration, the whole cube. This is exactly will be the QC. How many of you got this? QC.
Got it, sir.
Okay, good. Oh, got it. Very good, very good. Right. So then you will take this and substitute it. Basically, see, these are numbers. Say 1m concentration, 2m concentration, all these things will only come here. Okay, right. Maybe just one more example and then we'll do some problems. Okay, right. So now let me take, say, I think it should be easy, right? Okay, fine. So if I take She, guys, right? So if I take She, I know I'm going to have H plus bar H2, or depending on the reaction, it can be H2 bar H plus, depending on whether it's going to be cathode or anode. Okay. Now think and tell me what should be the N value for this reaction. If at all I have only She, what should be the N value for this? Or I'll write it like, okay, you first tell me what is the N value. Looking at the whatever is going to happen, the transformation, what should be the N value? How many electrons are involved here?
1, sir.
1, sir.
Look at it properly and tell.
2, sir.
2, right? How is it 2? Because say if I write the reduction reaction, for example, I'll write 2H plus will accept 2 electron to form H2. See, you have 2 here. It's not H, right? It is H2. So I will take 2H plus, and obviously it has to accept 2 electrons. The N value would be 2. Okay, and remember that H2 is a gas here. Okay, so if at all I want to write the QC for this reaction, okay, how do I write? Can you tell me if I want to write QC for this reaction? Can I write concentration of H2 divided by concentration of H plus squared? Is it right? Is it correct?
Yes, sir.
Okay. Now I have a gas. How do I talk about concentration of a gas? Okay, I think it should ring some bells. So instead of concentration here, what should I use then? If it is a gas. In general, in QC equation, if you have a gas, what do you use? Correct. We have to use the partial pressure of H2. So how do I write the QC value is like this. Partial pressure of H2 divided by the concentration of H plus squared. This is exactly how we write. This alone is something extra. Okay, since because we don't have H2, like on we cannot, it's really stupid to speak about concentration of H2 because there is no solute, there is no solvent, but I can use the active mass as the partial pressure. Okay, so whenever She comes, you should always take the partial pressure of H2 and the concentration of H plus. That's what you have to take. Again, depending with which will be the numerator, which will be the denominator, depending on the reaction, whether it's cathode or anode. In this case, it is reduction. So I wrote like this. If it was oxidation, I will write something else. Okay. I mean, something else means it'll H plus will go to the numerator and H2 will come to the denominator. Something like that. Okay. So this is what I wanted to mention to you. Okay. Now we'll do some problems. I think it's high time that we do some problems. What is the time? We have 15 more minutes. Maybe at least 1 or 2 questions will be able to. So just give me a moment. Give me a moment, guys. Okay. Okay. A simple question like this is coming to you, right? So they have given this cell representation. Mg solid bar Mg2 plus 0.2 m double bar Ag plus 10 power minus 3 m bar Ag solid. And they have given E naught Ag plus bar Ag is 0.8 volts and E naught Mg2 plus bar Mg as minus 2.37 volt. So what I want to know is the EMF of the cell is what. Basically, EMF of the cell means what? E cell is what I'm asking. Go for it. Okay, you have the cell representation, you have the E naught values. What you have to find is the E cell value. Go for it. I'll give you 5 minutes. Work it out. I'll also, after you finish it, then I'll do it. So guys, whenever you have this, write the cathode equation, write the anode equation, get the overall equation, then only you can speak about N value and the QC value. Do not just directly go for it. Just by looking at this, Mg2 plus is there, done, Ag plus is there, okay, Ag plus by Mg2 plus, no, it won't work like that. Okay, you have to know what is the stoichiometric coefficient, overall reaction, only if you find the overall reaction, then you can talk about QC, then you can talk about N. Right? Don't directly go for this. Write the overall equation. No matter whatever the question is, please write the overall equation.
Sir, I have a doubt.
Yeah.
Does this take place at 25 degrees Celsius? Sir?
Yes. That doesn't mean that they didn't tell you anything, but by default it is 25 degrees Celsius only.
sir.
Yeah.
So we should find the E cell value, sir.
Correct. You should find the E cell value, then you can go for E naught. I mean, so, yeah, correct. You should find the E cell value, but you first have to find the E naught cell.
Okay, sir.
Yeah, E cell is the end question. Yes, absolutely.
Sir, I got 2.44 into log of mg2 plus by ag plus square.
The values are given, right? What is Ng2 plus concentration given in the
Oh,
question?
okay,
And
sir.
what, yeah. Okay, just one more minute, I'll give you.
Sir, what is log of 200, sir?
Okay, you just keep it like that. No problem. I'll
Sir,
help you out.
Sir, then I got 2.44 into log of 200, sir.
Okay, fine. If at all you want log 2 value, right? Log 2 value is 0.3010. So from this, if you can find what is log of 200, you are welcome.
So that means you have to multiply 100, sir.
No, wait, I'll tell you, wait.
Log 2 plus log 100, right?
Log 2 will plus log of 100 will become, right? Yeah. Anyways, we'll speak about it. Wait. Log, this time log calculations, you have to be very careful, guys. Lot of times you can usually directly use your log books and find log of 200. But if at all you are not given the log books, like say in this kind of situation, still you should be able to do. That's the fun about it. Right? Okay, fine. Maybe I think I will do it. Right? Fine. So guys, the equation, we have to use Nernst equation, obviously. Right? Let me write the equation first for your reference. So I have E cell is equal to E naught cell, okay, minus, this is minus, there is no temperature, the temperature is not given, so by default it is 25 degrees Celsius, so it is 0.059 by n into log of QC. Okay, so first let me calculate this E naught cell. Okay, so for E naught cell, it will be E naught first I have to understand which is there in the anode, which is there in the cathode. Now from the cell representations we can understand, right? Because we always start only with anode. Obviously you can see it here, it's oxidation. And we end with a cathode, which is reduction. Okay, so now I have to know basically it is E naught Ag plus, because that is what is in the cathode, Ag plus bar Ag minus E naught Mg2 plus bar Mg. Again, why we write like this? Because we take only reduction potential and both the values are given to us. So this would be 0.8 minus of minus 2.37. So I think it should be 2.45 plus 2.45. Yes, that is my volts. Again, units are very important, guys. If you don't put the unit, half mark will be cut. Okay, so now 2.45 volts is the E naught value, E naught cell value.
Sir, 0.8 is 0.80, no, sir.
Oh, I'm sorry. Yes, correct.
3.1.
Yes, I'm sorry. I'm so sorry. Yeah, 3. Right. Thank you for correcting me. Okay, so it's 3.1. That's it. 3.17. 3.17 volts. Okay, fine. So we got E naught cell value as 3.17 volts. Okay. Now, all I have to find is now QC and the N value and substitute there. That's it. That's all I need to have. Okay. So for that, let me write the cathode equation and anode equation and write the overall equation. Okay, guys. Right. So I am doing all this just to, make you practiced. Nothing else. I can directly do the calculations in seconds anyways. Right. So in the anode, I have Mg becoming Mg2 plus by losing 2 electrons, and in the cathode, I have Ag plus accepting 1 electron to form Ag. Again, for me to make the number of electrons lost and number of electrons gained to be equal, I'll multiply this by 2. So this will become 2 Ag plus 2 electrons gives 2 Ag. So now the overall equation, now before that I can tell the n value. N value can I say is 2 because 2 and 2 are only getting cancelled. So n value is 2. That we got. So the overall equation now would be Mg plus 2Ag plus gives Mg2 plus 2 Ag, right? So from this I can write the QC now. QC would be what? Mg2 plus concentration power 1, because there is no stoichiometric coefficient here, this is just 1, divided by Ag plus concentration squared. Okay, so I think that also can be found out now, because they have given Mg2 plus concentration as 0.2 m and the Ag plus concentration as 10 power minus 3, right? So if I write it properly, so my QC will be Mg2 plus concentration was 0.2 divided by Ag plus concentration is 10 to the power minus 3. So 10 to the power minus 3, the whole squared will become 0.2 divided by 10 to the power minus 6, right? Okay, now if I bring this to the numerator, instead of writing it at 0.2 divided by 10 to the power minus 6, I can write QC as 0.2 into 10 to the power 6. Easy, right? I just go to the numerator, so the power plus will become, the minus power will become plus power. Or I can even write this as 2 into 10 to the power 5. Okay, fine. So we got the n value, we got the QC value. All we have substituted in this equation. Okay, so if I do that, I can write it down. So E cell will be equal to, we found out E naught cell as 3.17 volts minus 0.059 by n value we found it as 2 log of this value, log of 2 into 10 to the power 5. Log of 2 into 10 to the power 5. Okay, right? Fine. So now 0.059 by 2 you can easily calculate. Now let me tell you how do you calculate this particular value. Okay, guys, hope you remember this. Log of A into B. If I write log of A into B, how can I write it? What is the other way of writing it? Log of A into B.
Log A plus log B.
Correct. Log A plus log B. And whenever you have divided sign, then you put the negative sign here. Log A by B, I can write it as log A minus log B. Okay. So now what you have here is log of 2 into 10 to the power 5. So I can write it like this then. Log of 2 into 10 to the power 5. I can write it as log 2 plus log of 10 to the power 5. Right? Okay. Now log 2 value, I just told you it is 0.3010. Okay. Now how do you find this value? Is again very, very simple. Okay. Now remember this, guys. Log of A power B. If I write, how can I write it? B log A. Absolutely. Right. So can I write log of 10 to the power 5 as 5 log 10? Correct. The power will go here. Right, log of 10 to the power 5 will become 5 log 10. And what is the log 10 value?
1.
1, right? So
the answer
is 5 into 1 is 5, right? So what is now log of 2 into 10 to the power 5? Log of 2 plus log of 10 to the power 5, we found it as 5. So it is 5 plus 0.3010, which is basically going to be 5.3010. That is what is log of this value. So this entire value is now we found it as 5.3010, and then you can calculate it. That's it. Calculation you can do. Okay. Any question, guys? Right? Like if at all you are given the logbook, then you can find. Right? But if you're not given the logbook, also you should be able to find. That's the trick. Very simple. Very, very simple. Two formulas. Log of A into B is log A plus log B. Log of A power B is B log A. This alone you remember. Anything can be calculated. But again, you have to know log 2, log 3, log 4 values. But let me tell you another day, like how do we find the other log values? Okay, log 1 to log 10, you can remember easily. Let me tell you a trick to make you remember. Okay, guys, right? So first we calculated E naught cell from the given values, E naught of Mg and E naught of Ag. And then we wrote the anode equation, cathode equation. Then we calculated what is the N value. And from the overall equation, we found out what is the QC value. And all I did was substituting here and finding out the answer. And last thing we did was log calculation. That's it.
So what is the overall answer, sir?
Overall answer, let me give you the answer. This is short answer, like 119th question.
Sir, how would 2 into 10 to the power 5 came, sir? Shouldn't be 2 into 10 square, sir?
1 second, I'll come back to that. I'll tell you the answer first. 190. So the answer is 3.0. Where is it? 3.0134 volts. Okay, 3.0134 volts. Anybody got this answer?
Sir, should it be log of 2 into 10 square, sir?
Coming to that. The question I'm coming to that. But anybody got this answer? I'm asking.
Sir, I got 3.014, sir.
No problem. No problem. They will give you the mark, full mark. 0.11, 3.014 also you take, you'll get the full mark. Anyways, coming to that, right? QC, right? Okay, Kana. Say this is the overall equation. This you have any doubt? Overall equation is fine. Hello, are you there?
Yes, sir.
No. Whomever asked that question, how is it 2 into 10 to the power 5?
Sir, I understood now, sir. I didn't write the square symbol, sir. Sorry, sir. I understood.
That's the point, right? If you missed that, that's a common mistake. Lot of students do, and it's okay to correct it right now. Okay, you do a mistake now, you only correct it. But at the exam, if you do the mistake, then when you correct it, right? So then it is 2 to 10 to the power 5. Okay, I hope everybody understood. Is there any other question, people?
No doubt, sir.
Okay, cool then. I think we'll stop right here. Okay, and then we'll meet in the next class on next Sunday. Right. Thank you so much, guys. We'll meet again.
Thank you.
Thank you.
Thank you.
Thank you, sir.
Thank you.